manifold.
That's approximately the topic. Thank you for having me here. It's a pleasure to take off the mask. Oh, well, the only way of giving a token to get rid of it. So there were several four-dimensional talks on the beginning of the conference. I will drop to a lower level and discuss knots and three manifolds. But there will be some four-dimensional flavor somewhere left, but not that much. So what can we say about knots in general? Knots and three manifolds. We'll discuss how are they related and what do we usually want from them. There's one type of invariance of knots and three manifolds which I will be interested, especially so-called perturbative invariants. For knots, they're also known as finite type or Vasiliev invariants. For three manifolds, there's no united view on them, and there's probably 5 or 6 different theories which give similar results but not precisely the same. I picked up the name perturbative invariants because I would really talk about some invariants which come from the perturbative Chern-Simons theory, but you will never see and understand why are they perturbative in any way. So what about knots? You all know these standard pictures like this, which people draw on the board. And we still don't have a complete understanding of these objects. They're kind of too complicated. If you draw a diagram large enough, you cannot even say for sure whether it's an unknot or what exactly is it. And one of the reasons for that, that there's no good combinatorial, simple combinatorial description. And of course, lately, you can submit also a lot of pictures to any journal, but this is no good. If I will rotate it somehow or take it to another position, you'll probably not easily recognize it. So one of the big challenges there is to find some kind of simple combinatorial presentation of these objects. Several of these are known. One of these, which became especially popular in the last decade, are so-called grid diagrams. Which look approximately like that. You draw some square grid, whatever size, etc. 6, 7. And you place here some black and white dots in each row. So let me just start. Say black and then white. A certain law. So that in each column and in each row there will be exactly one black and exactly one white dot. And then you carry on like that. Let me carry on a little bit to see how it works. And then I'll explain how to construct a diagram starting from here. Black. Oops, I missed somewhere white. Well, that will be a real change. Okay, anyway. White. And I missed also black. Whatever. I missed some of these guys, and I don't know what to do with that, so let me just drop it because I don't really know how to fill it in. But basically what you start doing from such a picture, you draw vertical and horizontal intervals connecting these dots in one column and in one row. You just go on like that. And when you meet the path which you've already passed before, say, the vertical or horizontal, then there's a simple rule that the vertical interval always overpasses the horizontal one. So that's how approximately it will look like, say here, blah, blah, I don't know, where do I want to go from here, whatever, something, etc. Okay. I guess I should be going here and then here and then like this. And then. If I would do everything correctly, which I didn't, I would get a just trefoil, the same trefoil from which I started. Now, you see already the challenge in these diagrams, right? They're too big, the size is kind of uncontrollable. For the simplest trefoil, the smallest grid diagram is of the size 7. It's quite hard to work with them because the moment you switch just one crossing, and crossing change is one of the basic operations in knot theory, then things go bad, because then you should switch somehow this vertical and horizontal, so it's a bad movement. You have to change the size of your grid. Many bad things happen. Right? So we don't control it completely. It's very hard to draw. We don't feel how, say, knots change under one crossing change. The main reason why these grid diagrams appeared was because they're good for Legendrian and transverse knots. And then it turned out that they're also extremely good for Higard-Floer homology. And that's why they stay always up in the last decade. But they're pretty bad, say, for quantum invariants or finite type invariants. It's extremely hard to see a value of this invariant from some combinatorial encoding of this guy. There's another approach, which is to the opposite, very good for quantum invariants and finite type invariants. So far, it seems incompatible with Higard-Floer. We cannot see Higard-Floer there. And that's another problem with it, but which I will say in a minute. And it's called Gauss codes or Gauss diagrams. So these are much better suited to some computations for some small knots, for example. So what you do is the following. Let me just do something of that sort. So we'll take, say, figure 8 knot, and then what I do is I assume that my knot is oriented, and I mark here base point, and I start to follow my knot from the base point along, and as I traverse my knot, I encounter, of course, crossings, and I just enumerate them in the order in which I meet them. 1, 2, 3, 4. Right? So I met them as 1, 2, 3, 4, but then I carry on, and then I again encounter 2, 1. Did I? 1, 2, 3, 4. Okay. 4, 2, 1, and then again 4, 3. Obviously, I made each one twice. Such an encoding is called the Gauss Code. And you could start also from a planar curve. There's so far no information about over or under passes yet. So Gauss worked with these codes exactly for planar curves. But then, of course, if you want to incorporate some information about the diagram over and under passes, then you can just indicate somehow whether you pass over or under. So I would say here I passed over 1, and then of course I will pass under, and then here under 2, over 3, under 4. Okay, and that's how I go, under, over. So that was an alternating knot, so I go over, under, always. And if you wish, you can also add some information about signs of crossings. Signs of crossings which we usually assign to a node diagram are just assigned by the following rule. This crossing is called positive, this crossing is called negative. So if I look at my orientations here, now crossing points, then say this one will be the negative crossing, this will be also a negative one, while these two will be positive crossings. Okay. So you can just sprinkle them in here and write -1, -2, +3, +4. So this is called the decorated Gauss code, and it completely describes for you this knot diagram. You can reconstruct by a rather simple algorithm the knot diagram starting from this code. I'll not describe the algorithm, but it's really simple. What is the problem here is, well, these are some sequences of integers where it's clear that each one appears twice. There are certain rules, but if you just write such a sequence, it's absolutely unclear whether it will correspond to some actual diagram. There are many of them which are not realizable. For example, if I would, and I don't even care about signs and over or under passing, I cannot already build the planar curve, the underlying planar curve. For example, if I will write the simplest code of the type 1, 2, 1, 2, I would be unable to construct any diagram corresponding to this sequence. So it should be something with two crossings, right? So the only thing which I can actually construct with two crossings as a planar curve will be this. But then wherever I put my base point, for example like that, and however I orient it, I will see the sequence which is 1, 2, 2, 1. Right, so 1, 2, 2, 1. If I look at it as a cyclic sequence, as I should, of course, because I don't want to any dependence on the base point, then you see that 1s appear one after the other and 2s appear also. Building something like that is just impossible. So this is the main problem in this Gauss code, is that many of them are non-realizable. There's a certain way to say which ones are not, but to check it is quite complicated. And unfortunately, you cannot see immediately, and whatever standard algebraic technique you use to extract some invariants of these objects, if your technique is just purely algebraic, then it will not feel this realizability. So you will lose probably all the invariants which correspond to kind of real knots. But you will get it for some formal sequences of that sort, and they're called virtual knots. So the virtual knot theory was born out of the necessity to work with these sequences in pure algebraic manner without any questions about realizability. And I said here the word Gauss diagram. Well, that's an object which corresponds to such a code. It's very simple to construct. I just think about my knot as being an embedding of a circle, standard circle, into the 3 space, which I then projected to the plane and only kept some information about over-under passes in this plane. Right? And I just look at the pre-image. And I do the same as before. I mark the base point, and then I mark these points 1, 2, 3, 4 as I see them. So 1, 2, 3, 4, 3, 4. And I write it here. 1, 2, 3, 4, 4, 1. How many points do we have? 1, 2, 3, 4. Sorry. Okay. That was here, right? 2, 1. 2, 1, 4, 3. So there's an even number of points to show that they correspond, that these both say are preimages of the same crossing. I'll just connect them by a chord, like this. So I get a picture which would look like this. I can now remove all these numbers 1, 2, 3, 4, because I know the way these points are connected in pairs. And so it's a perfect matching of these points on the circle. But I would love to somehow keep the information about over-under passes. So I will orient all these chords from the overpass to the underpass. So if the first time here I passed over here under, I will orient it by adding an arrow on this chord. So now my picture will become already like this. Over, under, over, under. And I will equip these chords also with these signs which I see. So there will be minus, minus, plus, plus. So such an object is called the Gauss diagram. These are extremely well suited for quantum and finite type invariants. But the question of whether such a picture is realizable is at least bad, and whatever theorems we have, they usually are theorems for virtual nodes. So if we try to construct some quantum invariants or finite type invariants, these are guys which will work for all such sequences or diagrams. For example, the one which is not realizable, as I told you, whatever signs you put here, you cannot realize just this one. And this is a big problem, because we are usually asked about some existence or something for real knots. And we really just don't want to see all these virtual knots around. So the goal of today's talk is to introduce some simple type of combinatorial diagrams, which will be very similar in spirit to these Gauss diagrams, but all of them will be realizable. And the basic idea is very simple. Instead of the crossing change, which you would look like this, which is one of the basic moves in knot theory, which you see here as the inversion of both the sign standing on one of these chords and the direction of its arrow simultaneously. I would like to work with simple kind of clasps of that sort. Now if I start from something like this and I switch one of these crossings, then these will just fall apart. Okay. So instead of the usual crossings, I will talk about just these clasps. So now, what will be my object? It will be very similar to that, only now we'll look at a circle with a collection of chords. Again, let me just draw them. For these chords, I want some additional information. There will be no arrows here. There will be signs, just as before. So I will write here minus, plus, plus, whatever, on each one of them. So I drop these directions of arrows. But there's a new information, and it's kind of a height function. It's an ordering of all these chords. So if I look at it from the audience towards the blackboard, I think about these chords as being on different heights. The height function itself is unimportant, but the order in which I meet these is important. They're unlinked, so something having 3 of them like this, say, no, this is good. So what can be bad? Oh, this can be bad. Right? So something like this is impossible. It should be an honest order in between all of these. Right? So here, this one is higher than these two. And in fact, when 2 of these do not intersect, and they are in a neighboring order, right? So they are over or under the same set of other chords which they intersect. I don't really care about their ordering. I can just shift it.
So how do you do the drawing of the order diagram starting from these guys?
So what I do is, so let me call it, say, clasp diagram. And this word clasp will indicate for you the way I pass from here to a knot. Usual knot diagram, and it's all very simple. I just go and I draw my circle just as before, but now for each chord I draw a little ribbon, a very thin ribbon along the chord. So this is the core of this ribbon, but then I also insert a clasp somewhere along this ribbon. Okay. The type of the clasp, so there are 2 of them. This I will call the negative clasp, right? And the opposite one will be the positive. So let me say this. And this. So, whoops. This way you get a knot diagram. Always a knot, it's not a link. We studied from one circle, it's just a knot. Always. It's in this particular example. Let's see, what was that? It is the 6-1 knot. And the claim is, yes, so maybe I should say that, of course, I can do the same thing to get long knots. So long knots will look very similar, only my skeleton, for which I take this circle here, I call it a skeleton, will look now like just a line, but then I will have the same kind of type of chord. Like this. Can always draw them as half circles. For example, here the ordering is also clear from here. Minus, plus, plus. So it fits also long knots. And also long links. And for long links I do the same, only I draw several intervals. Like this. And then I draw here some chords like this. Okay. So this is a picture of a long link. So obviously all of these diagrams are realizable. Right? I just gave you a simple rule for that. There's another big advantage, and the big advantage is that if I just make a crossing change, before, say on the Gauss diagram, it was what? I had some crossing, it was a positive crossing, say going in this direction. Here I will get the oppositely directed arrow within opposite sign. Right? Here, such a crossing change, say here, will become much simpler because the moment I crossing change, they just fall apart and I can remove this chord altogether. So the basic move here is just, I had, say, this was a positive chord, and the move is just a removal of this chord. So of course it would be uninteresting totally if not the theorem. So I should say at this point that all results, non-trivial results for knots are joined with Jakub Mostovoy. So the first theorem, relatively simple, is that any knot type, any knot, can be realized by a chord diagram or clasp diagram. And you have a very simple algorithm for doing that, especially simple if you just start to work from some pure braid, or if you just have a closure of your braid, say flat closure of your braid, you can just immediately get this clasp diagram. I will not show you how it's done, but you should believe me that it's yes. Now, if we are interested, of course, in some working with knots and just with diagrams, we would like to understand when two different clasp diagrams correspond to the same knot. And there's a simple set of moves allowing us to pass in between any two clasp diagrams corresponding to the same knot, very similar to the Rademeister moves. So the first one I actually mentioned, and it's change of ordering of two consecutive non-intersecting chords. There's the other one, which is also quite obvious from this construction, and this is just that my ordering, about which we thought about as height, is actually just a cyclic ordering. The topmost chord I can put behind everything, right, and it will become the lowest one. So I will not write this as a move. It's just that the ordering is in fact cyclic. And the moves are the following. So there's the first move, kind of the analog of the Rademeister first move, we'll call it omega 1. When you take an isolated chord with plus or minus sign, whatever, and you just erase it. It's quite clear what happens then. There will be this clasp, but it will be isolated, and I can just unknot it. Similar technique works, of course, for framed knots, and for framed knots, you don't have this move anymore. The next one is the analog of the Rademeister type 2 move, and this is whenever you have two parallel neighboring chords with opposite signs, you can again just once again remove them. And the next one is interesting. And unfortunately it's not the usual Rademeister type 3. It has to do something with relations in the pure braid group. So it contains 4 of these chords. And it goes like this. So if you have one chord going here above everything, and then two more pieces here, and then you have something like this. And then with opposite signs, I never remember say the signs. For me, it will be just sufficient to have only one of these. I will use certain signs. Almost anything will do. The only important thing is that these two neighboring chords separated by that one should be of opposite signs. Then this picture, I will call this omega 4. So these two you can throw in onto the left. And now the ordering changes totally in the sense that whatever was on top now becomes on the bottom. But all the signs are preserved. And minus, plus, minus, plus. And if you would like to understand this more, then basically what is drawn here is a picture where I have a clasp here, see, like this. And then these two pieces I would like now to link in a funny way here. Now if I would like to redraw this picture in terms of some generators which I had, some simple clasps. Everything is combinatorial here, right? My chords are just straight. There's no linking or knotting. They don't go around somehow, they don't link one another or the skeleton, they just go totally straight. And so if I would like to redraw this one in terms of these straight ones, I would get conjugation of that one by two others. So this complicated link path would be a triple of these chords. And these are two different ways to view it. If you're not totally lazy and interested, you can just draw this picture. So here are all the moves which we have. And the next theorem says that if any two Clasp diagrams representing the same knot can be connected by a finite sequence of these moves. So now the knot theory just becomes the study of such chord diagrams up to these moves. Now, if you think that there's quite many of them, because on each chord I can put one of the two signs, and also I have a lot of different orders, well, it suffices, in fact, only to work with descending diagrams. So the ones in which, when you start from some base point, from this moment, each next chord which you meet along the circle will be lower than the previous one. But it's extremely, so you can take any of these by our moves to descending chord diagram, but it's extremely inconvenient to work with them. And to relay them by moves is like working with just pure braids, and if you just try to somehow take them to a nice position, then it's impossible to work. Okay? Now, let me just give you an example of a simple not invariant, which you will see from here. And examples of not invariants. Well, if you work with, say, long links of two components, then if you just look at the number of chords connecting them, and you count all of them with signs, and you should count them with signs, of course, because there's this parallel pair which is cancelled. So if you drop the signs, there will be 2 and 0. Doesn't work. But if you count these with signs, then of course it works. And this is just the linking number of two components. The next one would be not invariant, which is usually called V2. And it works like this. You look only at all sub-diagrams, which consist of pairs of chords. Now I draw them like this, intersecting, because I'm not interested in what exactly is above and what is below. The same for me. I will count all such. And if I had some signs here, epsilon 1 and epsilon 2, so here is epsilon, I'll count this with the sign which is epsilon 1 times epsilon 2. Okay. So you can easily check that if you count just the number of intersecting chords with these signs, then it gives you an invariant, and actually it's V2. You take it modulo 2, by the way. If you just count all of these as just a sign 1, right? Positive 1, you get a Z2 valued invariant, which is called the ARF invariant. So ARF invariant in this one is just the number of crossing chords, modulo 2. And if you know something about these oscillable finite type invariants, you'll notice that these two are the simplest finite type invariants. And in fact, in this way, we can construct very easily a universal finite type invariant. So it's the one which contains all finite type invariants. And to do that, I will just look at the following. I will look at, we call it maybe D. I will just look at the abelian group generated by such chord diagrams. Okay. So it will be a abelian group generated by chord diagram, clasp diagrams. I will then look at the formal sums of these guys with integer coefficients. And now we'll do the following. So first, you can define very simple map from these formal linear combinations of these diagrams to, again, formal linear combinations. I will only define it on generators. So I will just define it separately for each chord diagram, clasp diagram. And it's very simple. So any diagram goes into the sum, let me call this D, say, it would go into the sum of all sub-diagrams inside D. Okay, so here's an example. if I start from just such a diagram with plus and minus, then I will take it to, well, first of all, there will be this diagram itself, plus minus, and there will be one with a plus sign, and there will be one with a minus sign, and then there will be the edge. So this is quite a simple map here, and I would like to look at the following. I will look at the set R, which is generated by differences between the left-hand side of each one of these moves, which I had before, say only the one, minus the right-hand side and the same move. So the R1 will be just this minus that. R2 will be this minus that. Okay. Then I will apply my map, which takes each diagram into the sub-diagrams. And I will define A to be the set of all, say, ZD modulo I of R. Of each one. So
Omega 4, right?
4. This 4, of course, stands for the number of chords which participate in the move. So there's no omega 3. Whatever. So if I would like to, say, look at the relation which I get from I, and then I will look at the first move, omega 1, then what will I see? So in omega 1, the difference is in between having a chord, say, let me see here, it will be a little chord here, and nothing, right on this place, for simplicity. And sub-diagrams here will be this, the diagram itself, and then also when I drop this. Okay? Well, sub-diagrams here is only the empty one. So this difference after I apply an I is just tells me that if I have an isolated chord, then this is 0. So just look at the image and all these relations.
Well, this move is good, but in general, is it any tractable, this A?
Oh, yes. We can kind of very explicitly write you dimensions and the structure and generators of, say, up to A5. I see it, just, you can find it within, say, probably for A5 I would need about 20 minutes. It's a linear system of equations. You look at all these kind of ones, and you write the system. So with no computer, just on a piece of paper, I would probably need about 20 to 30 minutes. For A4, it would be 15 minutes. And so it grows, but all relations here are linear. So it's not very complicated. So you can encode it and have an algorithm, and just a problem, right? So we do know quite something about this. So I didn't tell you when I told you A4, A5, I didn't tell you what this is. So AN is just A modular, and I announced that all diagrams which have more than n chords to be 0. Okay. Diagram with more than n chords. Okay, so I just announced all this to be 0. Okay. So then I do know quite something about the structure of A1, A2, A3, A4, A5, have it for the complete knot table. And the reason I need this AN is, well, we have several other algebraic operations on AN, which I will not discuss now. But an interesting theorem is that kind of AN itself is a universal not invariant F finite type, not invariant, and that means so what did I say, and what does it mean that it's a universal finite type invariant? It's, just suppose that we have some finite type invariant of, maybe I'll say order n. If you suppose that I have some finite type of a Sylv not invariant of certain order n, then for each such invariant, I can present it V.
Sorry, but this, whatever, this Clasp filtration and Vasily filtration, you multiply by 2, or how are they?
This is quite interesting. So first of all, about some relation, say, to, so how complicated are these diagrams, right? Mm-hmm. How easy or hard is it to work with that? Just to give you maybe, I should draw some knot table. Well, it doesn't matter whether it's over or under, so I will just draw it like this. So plus plus, so this will be the trefoil. If I write here plus minus, this is figure 8. All knots for up to 6 crossings I can get from 3 chords now. So plus plus plus, say maybe minus, plus plus, and then 2 more, which will be this. So be under everything, plus plus plus, and whatever, plus, maybe minus, plus plus will be good. Okay, so these guys will be, let's see, actually write them down, I guess. So this is 5-2. This is 5-1. This is 6-1. And this is 6-2. And in general, if I draw knot table up to 9 crossings, there will be at most 3, 5, say 9 crossings. I will need up these diagrams with up to 5 chords. So on average, it's hard to prove something very clear here. So I can of course say that if it's the crossing number, from crossing number to the number of chords, I only can say that it's a linear mapping, but on average it goes into half number of chords and sometimes half plus 1.
So probably both directions you have an estimate, right?
I have an estimate which is linear. I can say in one direction it's this and another this, but it's kind of that's a gap. But just from the experience, for all nodes up to 10 crossings, it's still 5 chords. Right?
Sorry,
It's approximately the number of chords. It's half of the crossing number.
in these last 2 diagrams, the diagonal lines, the one is above another. So.
Yes, so I think that it's the top, the intermediate, and this one I drew kind of shorter to show that it's under both of these.
So, but in general, there shouldn't be three valent crossings.
No, but I can move it if you wish. Right, so this one is just the same as saying this, and then say that, and then this one will be placed here. Right? I just didn't draw it there. Drawings are too small. Okay. Now, if you don't care about these universal invariants and don't want to understand them and what is it and why, I can just tell you in different words, which are probably simpler. What does this mean? It means that all finite type invariants you can find and calculate in the following simple way. There's a formula of the types of, for each facility invariant of a certain order or not, you can calculate it in the following way. First, you encode this knot by such a clasp diagram. Okay, so sort of this, it's a clasp diagram. Any clasp diagram D corresponding to this knot. And then the claim is that for each Vassiliev invariant, you have a formula where you look at all subdiagrams, D prime inside D, and you count each such subdiagram with a certain coefficient, right? So D prime. And you just count the number of such subdiagrams appearing there. Now, what are these coefficients? As I told you, for example, yes, and here this VD prime is a certain function on the set of all these clasp diagrams, which vanishes on all clasp diagrams with more than n chords, right? So this is non-trivial only for something with less or equal than n chords. So when you sum here, it's a finite sum. So whatever diagram you have, say to get the invariant V2, you only should look at such subdiagrams. Right? If you want to calculate the V3, which is the next finite type invariant, you would look at subdiagrams which look like this. Well, actually, it doesn't matter over or under. You count the number of these. You always count these. If I don't write signs, it means the product of all signs sitting here, plus twice these. So again, independently on a height function, you count these with products of three signs, and then you take plus. Here it becomes more interesting, plus, plus, and minus, minus, minus.
Sorry, maybe I got a bit confused. I had an impression that if you know what is AN, right, so then not each of those diagrams should represent an independent finite type not invariant. Like, why
you have to go to generators of A, right? You have to know what's the dimension of A, and you have to pick the bases. Right?
Oh, these are elements of the base.
So here these say yes. So if I would look at A3, then you will see that A3 is generated by these guys, kind of by some no, maybe I should say it differently. A3 will be generated by, say, this one and whatever, plus plus, or say even plus minus would be good. So there will be two generators of that sort. And if I would look at the value of my diagram inside A3, it will split and it will look like, so we map from knots to A3 would look like blah 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 V3 of my diagram D type times this plus V2 of my diagram D times plus minus or something like this. Right?
Yeah, but I'm confused. So what is this complicated combination of
Well, you have relations in your A3, right? So the moment you assign something to this diagram, you automatically get some weights for the rest.
So that's basically bringing it to a basis.
This is bringing it to a basis.
Okay.
Okay, so these formulas, these coefficients, are just because we already know how A3 looks like, and we explicitly have chosen a basis there. Okay, so whenever I see such a subdiagram, I know that its weight, that it's twice this one, right, in A3.
Okay, but in principle, right, already those coefficients, they look slightly scary, and I mean, we should...
They grow, but this is kind of, it should happen, right, because we have many of these finite type invariants. But the advantage of this is that the moment you have to calculate it just once, right? The moment you have this formula and you calculated these coefficients, which are 1, 2, 1 minus 1 here, right? By the way, they're all integer, which is non-trivial. And this moment, you can calculate the value of this invariant on extremely complicated nodes, right? So you don't have to redo your calculations for every node diagram, right? So, in other words, kind of, which I try to say here when I say universal, is that for any finite type invariant, there's some formula of that sort, which involves only at most n chords. Say for V4, I will not write you what it's also it's not complicated. 7 terms in there. Now, in these formulas, there are top order diagrams, and then there are lower ones. These top order ones have to do something with Lie algebras. These coefficients, say 1 and 2, now satisfy the so-called 4T relation, which is that, try to do that. This minus that equals this minus. That's a well-known relation in the theory of finite type invariants, which is related to some bracket in an abstract diagrammatic Lie algebra, kind of universal Lie algebra in some sense. And you think that if let me just look at this piece here. Let me just formally put letter A here and B here. And I think about this pair appearing here as first acting by A and then acting by B. It's stupid, but it will give you some intuition. So that would correspond to AB. Here they appear in the opposite order, so that should be BA. So it's something like, kind of formally, Lie bracket. And this is the same. So if I would denote this bracket like this, so kind of A and B, there's a certain diagrammatic language to work with Lie algebras, and you usually denote it with these Y-shaped graphs, and you think even that A and B enter, and then the bracket goes out. I cheat a little, but not by much. And this picture should be symmetric, and this is another version of the same way. However, for these ones, it's quite a challenge to understand their meaning, and have some conjectural way to recover them from a quantum group plus some matrix, blah, blah, but I don't understand precisely which kind of structure should I have there. So these terms are governed, so these coefficients 1 and 2 are governed by a certain kind of Lie algebra, What do we have to do here is much more questionable, and I really am not sure about that. Okay, so 3 manifolds out for sure. Maybe I'll just tell you 1 or 2 words more about knots to explain which kind of problems can we solve with this funny encoding, in addition just to finite type invariance. Well, first of all, you don't see just a knot from such clasp diagram, but you see a knot together with its ciphered surface. So you actually do see the ciphered surface just from this picture. So should you have something like this, let me just draw for you ciphered surface. So suppose that you have some clasp diagram. How can I see the ciphered surface? Well, I just, first of all, I glue to this picture disk. Here, let me think. It's glued from below to this whole circle, right? And now I just add these ribbons here, like that, leaving these holes in here. So it's disk with ribbons. And if you think about this ribbon, it's actually, it's a usual ribbon together with ribbon added to it in the middle. Okay. So leaving a hole here is just the same as doing that. Right? So I actually do see, yes, and this twist here of this ribbon is the sign of this clasp, plus or minus. So I can see the whole, say, for example, Alexander polynomial or ciphered matrix from here immediately in terms of some matrix in which I see, I order my clasps in a certain way, and then I see everything just from signs of the intersections, kind of, and signs of each of the clasps. You can work with random knots. Surprisingly well, because it's kind of, what is a random knot on this language? If I encode it by this model, I just look at a circle, I take 2n points, and I just connect them in a random fashion, so it's a perfect matching. And then I sprinkle signs and this over-under, and I get a model for random knots, and we have some good results for random knots. And finally, say another one. Actually, there's some, on the knot space, there's some famous metric which is called the Gordian metric. The Gordian metric measures the distance between any 2 knots in terms of the minimal number of crossing changes in any diagram of the first knot to get some diagram of the second knot. Okay. So here in this sense, I can introduce a metric in a very similar fashion. I just say that the distance between 2 such knots is the minimal number of all clasp diagrams of the steps, and the steps are very simple. I just take a clasp ribbon and I remove it. Okay. And I want to start from clasp diagram corresponding to 1 knot, and by removal, get to the other knot. Okay. And it turns out that this metric between these 2 knots is exactly the same as this famous Gordian metric. And it's much easier to work with this one because you just remove, right? You don't switch. And again, we have some nice results in this direction. And there are more applications, and of course, 3 manifolds skipped. I should just say that there's a Serger representations for 3 manifolds, where each 3 manifold is encoded by a framed link. And if you use this kind of presentation for these framed links, you get some theory for 3 manifolds. And again, we have some version of universal finite type invariant, which conjecturally coincide with these perturbative Chern-Simons things, and we have some results in there. There are some beautiful relations between. Okay, so I stop here.
Thank you.
Any questions or comments?
How does the Kontsevich integral fit into this?
This is bypasses Kontsevich integral. That's exactly the point. Moreover, it's the Kontsevich integral works only for universal invariant, which is R-valued. For any other abelian group, there's nothing like that. Right, so this works universally for any abelian group. And it kind of bypasses it. Right? So the proof is actually very short. It's about a half page. It contains some information, but it's purely combinatorial. So whether I can prove that this is equivalent to Kontsevich integral, or can I get any of these guys, so far no. This is kind of what we are trying to do.
But if you're saying it is a universal finite order invariant, and the Kontsevich integral is also a universal finite order invariant.
But this uses, the question is, can we really do the same? So here we calculate some of the, this is actually an algebra.
Ask a question, but it sounds to me like universal property implies that they need to be invariant.
But
what?
Kind of in each one of them there's a hidden difficulty, right? So in the Kontsevich integral, it's just the Kontsevich integral. You have to do some integration which you don't know how to do. I mean, calculate efficiently Kontsevich integral, you can just in one case, right, explicitly, without kind of anything. If it's completely round, flat circle, I've never seen any calculations of Kontsevich integral for any non-trivial node. The only calculations there are from some abstract properties of the Kontsevich integral, etc. Right? So the Kontsevich integral, it's a thing which is incomputable. Right? In our construction, there's just this bad algebra which contains a huge linear system of equations to recover the basis. So there's difficulty in there. And I don't know how to explicitly see any relation between our calculations of some guy like this, right? These coefficients, seeing it in one particular basis, and these values of the Kontsevich integral. I cannot see it, I cannot see the passage. Right? I do know that both are universal, so they both give the same.
If I restate the question, by universality property, we do know that they are equivalent, or do we not?
Yes. Okay. This, yes, but this is the only one. I cannot, this is an abstract hand waving, right? They're both the same, yes. Now, if the question is, can I pass from this formula to some explicit expression for the Kontsevich integral, and to see how they fit, and why do they fit? I don't know how to do it.
Any more questions? Maybe just one small question in the same direction. So do you also have this theory for tangles? I mean, can you make some loose ends?
Yes. I can have loose ends. I can also use some graphs. I can work with trivalent graphs. I do have a version of this called what they call Y graphs and clasper theory. Javier Gusarov in these terms. This is. So it goes further, but of course I didn't say.
Okay, perfect. So, thanks again.
This is a good moment to thank the organizer.
Yeah, thanks a lot. It was a great pleasure to have everybody here. We still have lunch. And, well, please come in.